All right, hello everyone. My name is Joel Huther. I'm a senior undergraduate student at University of Kentucky studying physics, and today I'm going to be talking with you about my work on the Muon g-2 experiment installed at Fermilab. So just to motivate this experiment, just want to say that we've known for a really long time that the standard model is incomplete. We have a lot of different confirmations of this, but we need ways of probing this question, and how we can do that. One way that we do that, and the way that we do that actively at Muon g-2 is through a set of high precision experiments where we are trying to find some physical system where we know how to calculate everything about the system to a really high degree of accuracy. And then we also know how to observe it experimentally to a high degree of accuracy, and then comparing those numbers. If there's some discrepancy, then we're going to see some new physics explaining what's going on between why theory isn't matching with experiment. And that's exactly what Muon g-2 sets out to do. So the observable that we're looking to find out, the sort of quantity that we're punching out through theory and finding an experiment, is called the G factor, or really the anomalous magnetic moment of the muon. So a muon is a charged particle with spin. If we push it through a uniform magnetic field, it's going to feel this torque here. And that torque is set by this equation cross the strength of the B field. This G factor is really the key player here. This is the thing that we don't really have a good grasp on. Dirac said it should be 2. The standard model, which is our best theory of particle physics, says it should be greater than 2. And so what we do to account for that stuff, all that stuff that's bigger than 2, is we hold it all in this term called A mu, and that's the anomalous magnetic moment. Now, we know that all this stuff greater than 2 from the standard model should come out numerically to this value, and this is showing all the different, interactions that cause these numbers. But when we measure this in experiment, we see that we get a totally different value. So we need to ask ourselves, what's going on? Why are these two numbers different? And what we hope is that, hey, these numbers are different because there's additional interactions. Maybe there's dark matter interactions. We don't really know. Or maybe there's supersymmetries. We don't know what interactions are going on, but we certainly have reason to think that, hey, these two numbers are not the same. There's got to be some physics motivating that, and we need to figure that out. Now, this last measurement only gave us a 3.6 sigma deviation from what the theory predicts. This isn't really suitable for what we want to do. We want to get this over 5 sigma, just to use some statistical speech. And so what we're going to do that is that Fermi National Laboratory, so this was last done at Brookhaven, now done at Fermilab, the Muon g-2 experiment wants to reduce the experimental error of our measurement of A mu and get that so small that we can firmly say, hey, yes, we have over 5 sigma deviation from what theory predicts. So this is the beam ring installed at Muon g-2. Experimentally, what they look at is they shoot muons through this ring, and then they measure 2 frequencies of the beam's motion. They measure the anomalous precession frequency and then the Lamore precession frequency. Now, my talk is really going to aim at calculating this omega A, the anomalous precession frequency, and what goes into that. Because clearly, to get A mu, we're going to need to find omega A, and there's some stuff that goes into that, to say the least. So what is omega A? Omega A is just the angle between, well, it's the rate of change of the angle between the muon's momentum and its spin as it moves along this circle, magnetic, or this circular beam line. So we expect it to be a constant as long as we know the strength of the B field. It should come out to this number. And this would happen if we injected all the muons at just the right position with just the right amount of speed. But what we see in reality is this. So what's going on with that? this term right here is a pitch correction, and this term right here is an E-field correction. These corrections come out due to the fact that not all the muons that we inject into that beamline are at the magic radius or magic momentum. That's those perfect speeds and positions I was telling you about. And so we put E-fields in to kind of stabilize their motion to make sure that they all get into the beam, but this causes some motion of the beamline, and so these terms just sort of correct for that. And as you can see, here we have the ideal omega A, and then we're saying, hey, we're applying these corrections to that number. We can only calculate these corrections through simulation, and that's in fact what my work has done. The simulation package that I was using was GM2 RingSim. It models the experimental conditions to a T, uses a very rigorous statistical software framework. And so what we can do is we can calculate the pitch corrections through this expression. We can calculate the E-field corrections through this expression. We can get stuff out of the system from simulation that we would otherwise never have access to in a real experiment. So we can calculate the pitch and E-field corrections. We can also find a simulated observed omega A and see how those two things stack up. And in fact, that's what we're doing here. So what are the two things we need to get these calculations? Well, from the simulation, we need to extract the average square of the muon's position along the y coordinate of space. And we also need to have this ratio that's outlined here. This is basically a statement of how far away from the magic momentum and radius is our muon. That's basically what chi-e is when we run it on a simulation. When they run it on an experiment, it's a different analysis that they have to do. So we'll calculate CP and CE. We have to write code to do that. This is by no means a trivial endeavor. This took, hours upon hours. And we generate these histograms here. And so using GM2 RingSim, we came out to a pitch correction of negative 179 parts per billion, and an E-field correction of negative 227 parts per billion. And these are the histograms that show that. And then we extract omega A. We do that by plotting the angle between momentum and spin with respect to time. We can do that in a simulation. Fitting this function over it and using this function, we can just extract that parameter from a linear, least squares regression. Yeah, so we come out to this omega A. This is what those plots look like, that angle between spin and momentum. And so looking ahead, what I want to continue doing in my research is, looking at this relationship. This is how all these quantities are related. We have omega A observed, omega A that we should see ideally if everything was at the right momentum and radius. And then we have our spin corrections here. So I want to see how these two terms agree with one another. They're not agreeing with one another and completely yet the way I want to look at it. I need to look at that data some more. And also I want to get more muons. I want to do more events and get a more rigorous data set. And then the other thing that I want to do is play around with different function forms for the fit that might better account for the motion of the beam. We have reason to believe that this function is not what is not truly what this is. So yeah, that's next steps going forward. Sorry to blow through that. I'm on a time crunch here. They wanted me at 5 to 6 minutes. I believe I'm already at 8. So anywho, I just want to acknowledge my advisor, Dr. Fatimi, and she's been amazing, and Dr. Tarazona, who I was able to use some of his graphics on this presentation. So, and thank you all for attending my talk. Really appreciate it.